All right, let's get started. So our last class, um, we came up with this, right? Y'all remember? We came up with our currents and we figured out how to do this particular problem to solve for our voltage and our current. And it all hinged on this little part right here, knowing that that was 5 amps. Because once we knew that that was 5 amps, we were able to get the voltage drop through the 8 ohm resistor. And that meant pretty much everything could follow through from that. The one thing we didn't calculate is the power loss through here. So this supply right here, is it absorbing or delivering power? Let's just start with that part of it. Delivering, and why?
Because it's moving current to a positive voltage stream.
Yeah, in the direction of current, the voltage is increasing, right? So the only way you can get an increasing voltage in the direction of current flow means you have to get energy from some other location. How about the other power supply? VX or IX, I guess, is really the dependent one. Is that absorbing or delivering? Or can you tell? Why? Yeah, we can see this is plus to minus, right? Just because this says plus to minus here and here, that actually doesn't mean that it's positive to negative. That's just the assuming that that's what positive to negative is. But we confirmed that we have plus to minus in the direction as shown. So we actually have plus 8 volts here. So in the direction of current, we have an increase in voltage. So this power supply, we'll call it PIX, that's going to supply 8 times 1, right? Or 8 watts. And this power supply over here, that's also going to supply voltage. So we'll call it P60, or supply power, should say, is going to be equal to 120 watts of supply. Now, if you wanted to check those, you can do either I squared R for here, here, and here, or you can do V squared over R. It's totally up to you, right? Just really depends on what you want to do. You'll notice that I've got the current through the 8 ohm resistor, so I can use I squared R there. Or I can use the voltage drop, V squared over R, because I know it's 40 volts. It really just depends on what you wanted to do. All right, what about this problem? How do we do this problem? I'll give you 5 minutes to give me an answer. My computer over here says 9:32, so I'll give you 5 minutes. Active learning is the best. 5 minutes, go. I'm gonna shut the door, just getting a lot of noise from outside. That's slightly better. Make sure I'm recording. Got a couple more minutes. All right, what do you got? Anybody want to share their answer? You already know the answer, right? Or answers, plural. Anybody get the right answers? No? What happened? Simple series circuit. You're really good at circuit analysis. What tripped you up, if anything? Did you not have enough time? So what was the tripping? Were you not sure how to start the analysis? Okay, we're not sure how to start. Let's stand back and look at the circuit. And what we see is it's all a series circuit, right? And when we have an entire series circuit, we hopefully will recognize that we have one big loop, which means we can write a loop equation and use the sum of the voltage drops. So I'm going to assume a current direction here. And I'm going to do, for those voltages, I don't know. I don't know if it's plus minus. I'll just assume in the current direction that's shown. And I'm going to assume that there. So now I can do my sum of my voltage drops, negative 120 plus 30, and I should call that I, plus 2 VA, plus 15I, that's all of them. That's going to equal 0. So there's my one loop equation. Is there a problem with this one equation? Yes, sir.
Two variables.
Yeah, I wouldn't really call it a problem, but it's something that I can't just solve. So I've got two variables and how many equations? Just one, which means I need to write another equation, right? Or come up with another equation, or else I'm out of luck. I can substitute, which means I'm writing another equation, correct? Maybe?
I mean, it's the same equation, just with the smaller equation and then with the VA.
But I think we're saying the same thing.
We are.
You made the substitution sort of in the beginning, right? So what equation did you substitute?
The 59 in for 2 VA. I put 2 in parentheses 59, so it's 2 times 59.
Yeah, so what he's saying is he wrote an equation for VA equal to not to sorry, I times 15, but it's negative I times 15, right? Not positive. Because if I look at the controlling variable for my dependent source, its voltage polarity is opposite. So once I have that, then I can make my substitution in here, 120 plus 30I. And if I plug in VA, which is 15, negative 15I into that VA there, I get 2 times negative 15I, which is minus 30I, plus 15I equals 0. Now I have one equation, one unknown, and I is equal to 120 over 15, which equals 8. So here's the thing about dependent sources. Sometimes they can be scary, right? You always have to write one more equation when you have dependent sources. Have to write one additional equation, but here's the key. It's going to be based on the variables that you already have developed. Like he said, VA was equal to a multiple of I, right? Why did he say I? Because it's already in my equation as a variable that I need to solve for. So by adding in the variable I in my second equation, I'm not introducing a new variable. So I don't actually add an additional variable, I just add an additional equation. Okay, that's the most important thing about doing these problems with dependent sources. So hopefully what you can see, 120 times 8 is 90, 960, and that's supplying. And then 8 times 30 is 240. I think I have a typo here. That's not 1920, is it? The current is 8, so that should be 240. Oh, no, not 240. It's I squared times R, right? So 8 squared 64 times 30 is, in fact, 1920. This VA, I don't know what that is yet, so I'm going to go ahead and calculate the VA that I have over there. So VA, whoops, VA is equal to negative 15I, which is equal to negative 120. So the voltage that I have over here, plus to minus, is a minus 240. So it's in fact, it's actually the actual voltage is plus to minus 240 like that. Now I go 240 times 8, and I get 1920, but I'm in a supplying, right? Our negative number. And then I'm going to go ahead here and do my 8 times 15, or 8 I squared, 64 times 15, and I get 960 watts. All right. So the whole focus of this problem is right here, the dependent source. Very, very important that you see how to do dependent sources. Just add an additional equation. All right, another 5 minutes. You do this one. Yes, sir. Sure. I'll do 6 minutes. Remember, you don't actually have to write these down because all these PDFs are available to you. So if you bring the PDFs in advance, you can actually just bring it on a tablet if you have a tablet, and then you have this figure already there. So you don't actually have to copy them down. One of the things I don't want you to do during class is spend a lot of time copying things down, because at that point you're just transcribing, and I usually think it's better for you to actually be active, paying attention than just transcribing. But whatever works for you, it's fine. So.
also one of the world's deadliest. Introducing the eastern brown snake, native to quite literally every state in the land down under. And himself a silver medal in the no rope Olympics venom category, coming in second place for the most venomous snake in the world. It is worth noting the third and first place are unsurprisingly also both held by
This is why you
snakes,
shouldn't
because God hunt.
you shouldn't come to Zoom, you know what I mean? That's the problem with Zoom because you don't pay attention, right? You're listening to other stuff, not paying attention, watching YouTube videos. That's why coming to class, you're not going to be watching YouTube videos. Three more minutes. Last minute. All right. What'd you get? Did you get 2 volts, 60 amps, and 30 amps? Good. So how did you start this problem? Question or you get an answer?
Yes, it's an answer, but it's more of a question of how I.
Sure, go ahead.
So I saw that there was 120 amps, like that was going to be distributed along the circuit, and I saw that one of them was 30 amps, and I saw that one of the resistors was greater than the other. And so I saw the ratio between the two resistors. I found that was, is that something that we can do?
Sure. Yeah, you can absolutely do that. What was suggested is they saw the 120 amps and then they saw the rate, they did the ratios of the resistors to figure out how the currents distribute, which is kind of what I would do. But let's talk about it just in using some of the terminology that we're probably familiar with. So I have 2 nodes here, right? A top and a bottom node. And I don't have one loop, I have multiple loops. So this might be an opportunity to use a KCL, right? Do a nodal equation. But the first thing I'm going to do is recognize that the current in has to equal the current out. Well, I can see that I have 120 amps up and 30 amps down and only one node. So I'm going to redraw my circuit with only one current source, not the two, because I got 120 in and 30 out, which means I've got 90 amps really going into that node. And now this is 1 over 30. That's 1 over 15. Now I got a much simpler circuit because I got rid of one of the power supplies. And we haven't formally introduced a voltage or current divider yet in this class, but it's a review class, so hopefully you all have seen it. So we'll take advantage of current divider here, and then we'll develop it more formally in detail. But current divider says as long as you have a parallel set of nodes or two nodes, the current into the node divides amongst those nodes by the elements, by the element that not of interest divided by the sum of those. So that's going to be the I going through the 1/15 ohm resistor is going to be equal to 1 over 30 divided by the sum of those times the current in. Fractions within fractions, usually better to go ahead and do common denominators. So common denominator in the denominator is 30. When I put those together, and tell me if I do this too fast, I have 3 over 30. Did I do that too fast to how I got the common denominator? Invert and multiply, and I'm left with 1 over 3 times 90, which is equal to 30 amps. Now I can certainly do current divider for the other one, but why would I? If 30 amps is going through here, I know that 60 has to be going through there, right? I don't even have to check that one. You can do a current divider, but you just intuitively know that it has to be 60 amps. Questions on that?
I did it a little differently.
Yeah, there's a million ways to do that, but sure.
Yeah, so I did do KCL. So, but instead I just had VA over 130 plus 30 plus VA over 115 minus 120 equals 0.
Yep, that's
for VA.
Yep, that's perfectly fine. Yep.
And that gave me the voltage, and if I know the voltage, I can just VA over I equals VA over 130 back in, or
Yep.
115, you get the current out.
Yeah, what you'll find is the way that you did is you are actually setting up how to do current divider. So you did it all the way if you wanted to formalize it, and if you didn't know current divider. But if you take a look at your end approach, it actually is essentially current divider. Go ahead.
Yeah, but you can also shrink the circuit down even smaller to get just the voltage to then solve using parallel resistors.
So the comment is you can shrink the circuit down so you can combine the resistors if you want. Sure, you can absolutely do that. I don't suggest you do a lot of work to do series parallel combinations of resistors unless you're looking for Thevenin equivalence, because you start to lose information about your circuit when you do that. Okay, it works perfectly fine, but you might not be able to calculate like the power loss through something if it's buried inside of an equivalent resistor. So just be careful. That works fine. And it's a lot of work too, or more work, I think. So yes, you can certainly do it that way, but I just showed you what I think is the most efficient way to do it. So that's what we did, right? We had a bunch of current sources. This one shows 3, and we put the 3 into one equivalent current source, and our results are exactly the same. No change in our results. So we can use KVL to show that resistors sum as shown, and let's do that. Let's do a simple series circuit. Okay, we'll just do two, and then you can put 3 or 4 or 5. So we're going to do a loop equation. This is my current. And what we have is negative V is our plus IR1 plus IR2 equals 0, correct? Negative V plus I times R1 plus R2 equals 0. If I bring the V to the other side, and R1 plus R2 equals V over I. Does everybody agree with that? So the concept of equivalency is I can replace however many resistors I want with a single resistor, okay? With any single resistor, and I get the same result. So if I wanted to build an equivalent circuit, at least seen by the source here, then I recognize that V over I has to be equal to R equivalent for Ohm's law. Whether it's the right-hand side or it's the left-hand side. Right? So what we see is R equivalent is R1 plus R2 plus R3, on and on and on. And that's how you prove the whole concept of resistors in series. It's actually a very specific application of KVL, right? Because we proved it by doing Kirchhoff's voltage law. Okay? All right, 6 minutes. Can you do this problem here? So first case, you want to go ahead and simplify the circuit down to essentially a Thevenin equivalent. And then if you want, you don't have to, if you want, you don't want to, you can move things around if you want. It's totally up to you. Couple minutes. All right, let's do it. So this circuit, you immediately want to do KVL loop, correct? Which you always can do that. But sometimes if you can stand back and realize this circuit actually might be able to be simplified, maybe taking some advantage of some of the stuff we've gone on in this class might make it easier. So I'm going to regroup all the power supplies, and I'm going to recognize that that's not going to match the exact original circuit, but all I'm looking for is the power supplied by the 80-volt source, right? It's really all I need to do. So the equivalence is this current here has to be equivalent. It has to be flowing through all the elements in the circuit. So I'm going to regroup the three power supplies and connect them together because they're all DC, and then I can add and subtract. And then I'm going to go ahead and add and regroup the three resistors. So now I go minus to plus, increase of 80 volts, minus to plus, increase in another 30 volts. So now I'm at 110 if I'm measuring from here to here. Then I drop 30 volts. So from here to here, I have 80 volts, right? Or 90 volts. That's 20 volts down, sorry. So that's the first part. And then the next part is this voltage here is 90. Now I'm just going to sum those resistors. 10 plus 7, 17, plus 5, 22, plus 8, 30. So my circuit now is 90 volts and 30 ohms. And the current out of that supply is exactly the same current over here. So I is going to be equal to 90 volts divided by 30 ohms, which is equal to 3 amps. That current here is 3 amps. And now I can calculate P out of the 80-volt supply as just V times I, 3 times 80 volts. Anybody else get that result? Similar process as you do loop equations. Similar process? Okay, good.
I did the same exact thing.
Oh, good. Okay, perfect. Okay, so let's use another approach to use KCL to make our lives easier. And this hopefully is what Arthur was talking about when he did his approach. And let's actually see if it comes out. So I'm going to go ahead and I'm going to use nodal analysis, just like Arthur suggested, to start. So my nodal analysis means I've got, and I'm only going to look at two sources, or two resistors, R1, R2, and this we'll call I. Now, the voltage drop across here, we'll just arbitrarily call it VA. So the sum of the currents into the node is the sum of the currents out of the node. We'll assume, for lack of better knowledge, that the current is down out of the node. So the current into the node is equal to I. The current out of the node is V over R1 plus V over R2, correct? Now let's go ahead and combine those terms. So we have V times 1 over R1 plus 1 over R2. And we've got fractions over there, so sometimes it's better to work with them. So let's do common denominator. which hopefully what you see, the common denominator has to be the multiple of those, R1 and R2. And this becomes R2 plus R1, right? So now I'm looking for V divided by I, right? Which is going to be equal to R1 times R2 plus R1 over R2. That's V times I. Over here is the equivalent circuit. So we know that V divided by I over here is R equivalent, which matches our result over here. So R equivalent is equal to that, right? Now we combine them into one value, but we could have kept them like this, correct? So we also could say it's equal to 1 over R1 plus 1 over R2 raised to the -1 power. Either one would work for us. What's that?
1 over the 1 over.
1 over the 1 overs, exactly. Now, sanity check our work. Remember at very first class, we talked about checking for units. Do our units jive here? We know when we sum them in series, we had R1 plus R2 plus R3 on and on and on. So that's an ohm plus an ohm plus an ohm is all ohms. Over here, we're multiplying and dividing. So do we still end up with an ohm? Well, this has ohms. This has ohms. They're multiplied by each other. So that's ohm squared. And I divide that by ohms plus ohms, which is just ohms. So ohm squared divided by ohms is equal to ohms. So our work checks out. So if you use elements in parallel with each other, and we'll actually, as you go further along, we'll actually hardly ever do this. But now what we see is for two resistors in parallel, you can do product over sum for combining resistors. If you have more than two, don't even try to do the product over sum approach. Just do the 1 over plus 1 over plus 1 over and 1 over that, and then that's much, much easier for you. Okay? So that's our shortcut. One thing when you're checking your results, when you have resistors in series, the resistors in series should always have a greater resistance than the smallest resistor that you have. I mean, the largest resistor that you have. All right? So if you have a 3 and a 4 and a 5, and your R equivalent is 2, you probably made a mistake. It's got to be greater than at least 5. Over here, it's the opposite. Your parallel resistance should be less than your smallest resistor. Does that make sense? Everybody think it makes sense? Good. Somebody tell me why it makes sense. If it makes sense, tell me why it makes sense.
Because it's going through the smallest resistor and some's bleeding over through the other one, so it's going to be less.
Maybe. I'm having a harder time envisioning that. Anybody else want to expand on Arthur or come up with their own? Come on, you all said it makes sense. Make it make sense to me.
Well, you know that the smallest resistor is the smallest resistance, and then you have other resistors that are allowing some current to go through them. So overall, the circuit has less resistance than that smallest one.
I think you're now saying what I was hoping you were going to say. All right, so when I put resistors in parallel with each other, right? Aren't I just adding more paths for this current to divvy up? More paths mean less resistance, right? More places for the current to go than just a single resistor. So I had darn well better have more current going through, which means a smaller equivalent resistance, than any of the single resistors, right? Got to, because you're just providing more paths for those electrons to flow through. When they're in series, now I've just made it harder for the current. Each resistor I add makes it harder for the current. Harder for the current is another way of saying more resistance. So putting more resistors in series means it's harder and harder and harder for the current to travel through the circuit. So that's how it makes sense to me, right? So when they're in parallel, I got more paths for the current to go. It should be easier for it to flow, which means the resistance is effectively lower. More resistors in series mean it's more arduous for those electrons to flow through, so my resistance has to increase. That's how I make it make sense. Here's voltage divider. You can actually derive the voltage divider approach. Yeah, let's derive it real quick. It's pretty easy. So we're going to go ahead and do a KVL loop around here. So negative V plus I R1 plus I R2 is going to be equal to 0. So I is equal to V over R1 plus R2. Everybody agree with that? That's the current. Now the current through R1 is going to cause a voltage drop in that direction. So V1 is going to be equal to the current I times R1, which is equal to V divided by R1 plus R2 times R1, which is equal to R1 over R1 plus R2 times my voltage. So voltage divider is just a derivation, it's using loop equations or KVL to go ahead and solve for that. Okay. But here's the key thing about using voltage divider, and most people forget this. You can only use voltage divider if you have a series circuit. Only works for a series circuit. And you need to know or be able to obtain the voltage across the entire series circuit that you're going to use voltage divider for. Okay? You need those two things. Otherwise, you can't do it. And hopefully you see that over here, because if we don't know a closed loop, right, we don't have that whole voltage, then we can't start off our voltage divider. And it has to be a series circuit because that current that we used or calculated is going through all those elements. All right. Can we do 5 minutes on this one? Short circuit. Is this too much active learning, making you do all these circuits? One more minute. All right, what'd you get? Did you get 4 sine t? How'd you do it?
Probably 63. 6 ohm and 3 ohm resistor,
Put those in parallel.
and use voltage dividers, then find the voltage over the 2 ohms parallel to it.
Okay. So first thing we did is we did R equivalent. We did product over sum. 18 over 9, which is equal to 2. Our new circuit is here. And now we can just do voltage divider. So voltage divider is take the voltage that is applied across the series circuit, 12 sine t, multiply it by the resistor of interest, 2, and divide by the sum of the resistors in the series circuit, 4 plus 2. So that equals 12 sine t, 2 over 6, which is 1/3, which leaves me with 4 sine t. Okay. Parallel is going to be application of current divider, which we kind of cheated and used already. But let's do the derivation here. So we're going to use nodal analysis here, which says the current going in has to be equal to the current going out. So I, which is in, is going to be V equal to V over R1 plus V over R2, which is equal to V times 1 over R1 plus 1 over R2. That's the current going in, right? So now, if I want to solve for any current, let's just say R1, I'm going to take that voltage, which is I, can't write here, I divided by 1 over R1 plus 1 over R2. That's the voltage that I see there. And I'm going to divide that by R1, right? Because V divided by R is going to give me the current going through there. So I got a lot of fractions to work with. So let me go ahead and do this first. Let's just do it this way. 1 over 1 plus R, 1 over R1 plus 1 over R2. We're gonna do common denominator. So we have R2 plus R1 all over R1, R2, which is equal to R1, R2 over R2 plus R1 or R1 plus R2, right? Just depends on your perspective. Now, I'm going to substitute that into here, and I have I R1 is equal to I divided by R1, R2 over R1 plus R2, and that whole thing is divided by R1. The R1s will cancel, and I have R2 over R1 plus R2 times my value of I. So again, this only works if it's a parallel circuit and I know the current going into the parallel circuit. It's got to be a parallel circuit because that voltage is common amongst those two elements. Okay, so current divider is just, again, a specific application of ACO. All right, I'll give you 4 minutes for this one. Find I3. Find I3. It's the same problem we just did, but now we're looking for, excuse me, our results here. Couple more minutes. Okay. Anybody get the answer? One person, two people? How'd you do it? Go ahead.
Use the same voltage, over the parallel resistance that we got from last problem and just did the Ohm's law over 3 ohm resistance.
Yep, that's the easy way because if you looked at the previous problem, we knew that that was 4 volts. But let's pretend we didn't know it was 4 volts. Is there another way you could do it? I think if we put those in parallel, solve for the current from the power supply, which will be the current into those two parallel resistors, and then use current divider, we can get our answer. Again, nothing wrong with what he did. It was predicated on knowing what the voltage was. But let's try to get it just directly. We don't know what that is. So we know 6 in parallel with 3 is 6 times 3 over 6 plus 3, which is equal to 2. So our circuit now becomes 12 sine t 4 and 2. And the current here, I, is going to be equal to 12 sine t over 6, which is equal to 2 sine t, correct? Now, I'm going to redraw my circuit. And this is 6 and this is 3. How do I redraw my circuit to show the 2 sine t is going in there? I can just show it as a current source, can I? 2 sine t. So now if I want the current going through the 3 ohm resistor, I'll use, we'll call it R3 for lack of a better term. We're going to be our applied current into the node, 2 sine t, multiplied by the resistance not of interest, or the one of not interest, 6, over the sum, 2 sine t, 2/3 sine t. Okay. So there's a million ways that you can do this, right? More than one way to skin a cat. You can pick whatever one you like to do. A couple last things. I think these are the last couple of slides I have about material. So we talked about in our study of classes, we always assume that our voltage sources are ideal, which means they can provide as much voltage or current regardless of the load. In the real world, we can't, those just don't exist. And so how you model voltage sources or generators, or even batteries for that matter, in the real world is an ideal source. And in series with that ideal source is a resistance. And as you increase the load, the voltage on the terminals of whatever you're trying to connect to start to drop. And we're going to assume that it's a linear drop. Okay. So you can see here, if I have a source that is shown over here, as I start to increase my load, so if my IL goes up, my voltage starts to drop, heading back to 0, right? So at my max load, my voltage goes to 0. If I run open circuited, which means my current is 0, then my voltage is whatever the source voltage is. All right. Do the same thing for a current source. Current source, when the load is 0, which is another way to say there's no voltage there, right? So if there's no voltage, there's no power demand, then my output is going to be at my ideal value. Once I start increasing the voltage till I get to its nominal rating, at that point, my current is no longer going to be able to be supplied. So I peg my current down to 0. And the only reason why that works is because an equivalent circuit means that that current is bleeding off through that direction, okay? So essentially, when you have an infinite load, all the current goes into your equivalent circuit. Now, in the real world, this doesn't exist, right? These are just equivalents to make our circuit analysis assumptions about ideal voltage and current sources work, okay? So that's why a voltage source, it has it in series, where a current source has it in parallel, okay? All the current bleeds through that parallel resistor in a current source. In a voltage source, all the voltage is dropped across that source resistance. And that's how we actually model them in the real world. Questions on all this stuff? Probably a little fast than what you were exposed to in the past, but hopefully it's all review. Hopefully the stuff that we did today, nothing is new. And there was one other thing I did intentionally, and I don't know if you all noticed it. Did you ever see me bring out a calculator? You don't need to do a calculator. A lot of these problems. And it behooves you, for what it's worth, it benefits you to spend a little bit of time trying to be able to do the math numbers in your head, because it actually, you can sort of sanity check. Does this make sense? When you're doing your calculator, you're just punching in numbers and you're getting a number on the screen, right? It doesn't give you a feel for what's happening. But by doing them in your head, you're like, yeah, this makes sense, or no, this doesn't make sense. And so it gives you that, sort of appreciation of how to do that. So trying to do that as much in your head is going to benefit you. We will start to be doing stuff more and more with MATLAB because I'm going to be writing multiple equations. And instead of doing substitutions and trying to do it that way, I just write all the equations out. So I'm going to show you how to do a lot of linear algebra and writing simultaneous equations. And we're going to take care of matrices to go ahead and give us our answers and then hopefully go from there. So what I try to do is I always go back to like the very basic fundamental things. Thevenin, Norton, which we'll start getting into in our next little bit, mesh equations, loop equations, because if you can get through those basic concepts, it really helps enhance your understanding of the material. So questions?
I want to have a general question.
Sure.
When are you, for the Zoom, like recordings, when do you normally have them posted during the day?
Well, so I try to get them posted within 2 to 3 hours. Well, let me back up. It generally takes Zoom, because all these you saw were recorded on them. It takes around an hour to an hour and a half, sometimes 2 hours for Zoom to do the processing of the video, because they're doing all their stuff, whatever has to happen. And I don't get a notification that a link is ready until between 1 to 2 hours typically. So I get the notification, then I download it on my computer, and then I upload it to YouTube. And so YouTube takes however long they need to process stuff, right? It depends on how many people are uploading stuff. But once I upload the stuff to YouTube, I actually copy the link and then I make it available in the course folder for the class. So the link is there, but if you click on it, YouTube might say, sorry, we're still processing. Or if it does make it available, it actually will say it's standard definition. So if you're trying to look at some of the stuff and it's not clear, it's because it's a standard definition. And usually a couple hours after the standard definition one is available, YouTube has gone through and done the high definition processing. So usually within like 4 or 5 hours, all the high definition stuff should be available. But that's predicated on a lot of things happening with processing and all that stuff. So that's the general rule of thumb. But the 2 videos from last week were up and available, right? Yeah, it's just I can't do it instantaneously after class. It just takes.
Thank you.
Sure. Any other questions? Feel good? Ish? Well, one of the things too is we're going to start doing more and more review, but we're also going to start moving into new material or things or approaches to look at it. So it's your responsibility. I'm handing the buck to you to tell me when we're going too fast, too slow. You need to let me know. Because I can do this stuff pretty confidently. I've been doing it for a long time. So I have a high confidence. And so for me, something that seems obvious may not necessarily be obvious to you all. And that's okay. That's the way it should be. So if something doesn't make sense, hey, wait a minute, and you go back, slow it down, explain it differently, et cetera, et cetera, et cetera. Then, you know, that's when the thing will work. But that's your responsibility. You have to let me know. I try to read the class a little bit, try to look at people's eyes, try to see if they're writing and all that stuff. But sometimes it's not obvious. Like if you are done writing, it could be that you don't even know how to start tackling the problem. So again, that's something that you all have to check in. Last thing I have for today's class is your first homework assignment is assigned, right? It will be available at about 11. So that's due in a week. And it's basically just doing some of this stuff. So you'll just submit that to Brightspace and we'll go from there. TV Land, any questions? No questions? Oh, question here.
For, you have a lab this week?
Yes. Yeah, you have a lab on Friday.
And pre-lab, like.
Yes.
That's just all.
It's on the lab handout. So there's a pre-lab there. Yep.
And it was,
It'll be a multi-sim one. Yep. Where you're using a Whetstone Bridge. Yep.
Sure.
Anything else?
Like,
Yes. So the idea is in some labs, if you can do a pre-lab component, you kind of come in the lab knowing a little bit about what is going to be expected. So you're going to do some pre-lab calculations to make sure, okay, this is what I'm expecting to get when I do the simulation. So instead of having you just do calculations in lab, trying to check your work, it's like you already know what your results should be. And then when you get to lab, you just confirm. So it makes your lab time more efficient. You can do that in like these labs here. That's not too bad because there really is just a bunch of circuit analysis that we all know really well. It's harder in other classes where it's like, I can't do the calculations. I'm not exactly sure what to do. So that's where it depends, like in your past, you may have had pre-labs and you may not. Usually the lower level classes, it's easier to have pre-labs. Anything else? Going once, twice, 3 times, and sold. All right, everyone, have a great day. See you all on Thursday. Take care.
Thanks, Paul.
Thank you.
See you later.
Take care.